Good day students. In this video, we are going to verify the Kirchoff's laws using PSIM software. So before verifying the laws using the software, let us recall what the law states. So Kirchoff's law consists of two laws. One is Kirchoff's current law and another one is Kirchoff's voltage law. So Kirchoff's current law states that the current entering any junction is equal to the current leaving that junction. So that junction may be a nodal point of the circuit. And this law is also called as Kirchoff's first law or Kirchoff's point rule or Kirchoff's junction rule or nodal rule. So what is the summary is the algebraic sum of currents in a network of conductors meeting at a point is 0. So to make it clear, when I am having some particular node and there are many currents entering into the nodes and some currents are leaving from the nodes, let me give a name for each current flowing through each path. From the definition of this particular law, what we assume is the current entering into this particular node is I1 and I2 and the current leaving this node is I3 and I4. So based on Kirchoff's current law, the expression will be I1 plus I2 will be equal to I3 plus I4. So this is Kirchoff's current law. The second law is Kirchoff's voltage law. So here in Kirchoff's voltage law, the sum of all the voltages around a loop is equal to 0. So it's a simple law. So in Kirchoff's voltage law, the sum of all the voltages around a loop is equal to 0. That is, if we are having a circuit like this, so I am having some plus to minus battery source, and if I am having some resistances and it is a closed loop, we know the direction of current will be like this, and if the direction of current will be like this, the drop across the resistor will be measured using these potential. So here if I mean this potential as V1 and this potential as V2 and this potential as V3, now V1 is a potential rise which rises from minus to plus. If you consider V2 along the flow of current path, the direction is plus to minus. So it is a potential drop. So here it will be considered as a potential rise, minus to plus, here plus to minus, it will be a potential drop. Again in the direction of current flow, here if you see the drop across this resistor, the second resistor is plus to minus, so this is also a potential drop. So according to this Kirchoff's voltage law, our V1, the potential rise will be equal to potential drop, V1 plus V3. Or we can say the sum of all the voltages around a loop is equal to 0. So if I consider V1 as positive, then V2 is in opposite side, so it will be minus V2, and V3 is also opposite, so it is also minus V3. So this is the sum of all the voltages across the loop and it will be equal to 0. Both the equations represent the same thing. So we can define Kirchoff's voltage law at the sum as the sum of all the voltages around the loop is 0, or we can also say the potential rise is equal to potential drop in a closed loop. So considering this basics, let us see a simple circuit to verify the Kirchoff's laws. So here there are two loops. So considering the Kirchoff's current law in this particular node. So I am considering this node. So here there is a voltage source and there are 4 different resistance values. So here in this case, if I consider this point as a point P, so at point P, as this is the source, the current direction will be in this direction. So the ammeter polarity will be like this and the drop across this resistance also will be like this. So I am assuming that same current will be flowing in this direction in this loop and the current is flowing in the second loop in this direction. So if you assume the directions like this, then according to Kirchoff's current law, the I1, so this is the only entering current into the point P. So I1 is equal to the sum of current leaving from this point. So this is the current leaving from this point is this I3 and this I2. So I1 will be equal to I2 plus I3. So if this equation satisfies, we can say the Kirchhoff's current law is satisfied. So this is the verification for KCL, that is Kirchhoff's current law. For Kirchhoff's voltage law, let us consider one single loop. So I am taking the first loop and I am just mentioning the current direction in this direction. So if I mark the polarity of all the devices, here it is a battery, this is plus minus. So the current is flowing through this path and the drop across this resistor will be in this polarity and the current flowing in this direction in R2. So the polarity across R3 is like this. So we are neglecting the resistance on the ammeters. Then what we will be getting is the potential rise. So the potential rises from this low tension DC direct current source. So this 36. So this is a potential rise, 36 volt. It is equal to the current flowing. So if I am considering some current flowing through this particular resistance and the drop across this VR is VR1 and the drop across VR2 is, and the drop across this R2 is VR2, then this 36 will be equal to the potential drops in this loop, that is VR1 plus VR2. So this is for this first loop. So this is your first loop. So considering the second loop. So the second loop is considering for the same circuit. I am assuming the current flowing in this direction. So the drop polarity for this R3 is in this direction and the voltage drop let me write as VR3. Here the current direction will be like this and the drop polarity will be like this and let it be VR4. So consider this second loop. So this is loop 2. So for loop 2, if I see the polarity of VR2, VR3 and VR4, the only polarity of VR2 is varying. So VR2 will be equal to VR3 plus VR4. So this side it is in polarity minus to plus in the direction of current, and this side the polarity is drop of in the resistor is plus to minus in the direction of current. So I am just writing the polarity in the direction of current. So this is just a key point, and it is not a basic rule to be followed to write these equations. This is one of the hint that you can use to write the equations. So we are going to check whether these satisfies using the simulation. So let me open a PSIM. So now I have opened the PSIM software, and this is the home page of the PSIM software. So in the PSIM software, now I am clicking a new icon and a new work area has been produced. So here in the PSIM, if you see, in the bottom we are having so many components that we are frequently used in electrical circuits, and in the top we are having some file, edit, view toolbars to work out on the things. So now I am going to try to simulate the same thing. For that I require a DC source. So I am clicking the DC source and taking the DC source and placing. And then I require 4 resistor. So resistor is here. So I am taking 4 resistance. I am fixing the resistances in its appropriate place. So when you right click, the direction of the resistance will change. So I am just formulating the circuit. Then I need ammeter to verify the current law. So I am selecting the ammeter, and the direction of ammeter is here plus to minus. Here I am just want to mention record the I3, and here I want to read out the I2. So this is the ammeter. Then I want to give the connection. So to finalize the connection, here I am clicking the wire so that I can connect the remaining part of the circuits. So now it is just a simple pick and place and drag it. So to complete the circuit, I am just connecting a ground, attaching the ground to the negative point. So here, after finishing the circuit, we have to enter the values of each and every components. So I need to give 36 volts for the DC. For that, I need to click the select. So the select component will select each and every component. So I'm clicking that particular component so that that particular component will be displayed, and we can set the amplitude for that VDC. So I'm fixing 36. So I'm displaying it in the circuit. So I'm displaying this is a VDC and the value is 36. Ammeter is I1. I'm displaying it as in the circuit. And this resistance value we are going to fix as 185. And this is our R3. And this value is our R2. And the value is 185. Right. So this value we need to set. This is our R4 and this is also 185. So this ammeter is we have treated as I3 and this is I2. Fine. So we have give all the name. If we want to check the Kirchhoff's current law for this particular, let me simulate. So go to simulate and run simulation. So here the variables available is coming and variables for display we can add. So I want to display all the things. So I am selecting all the 3 current values and adding to the display and clicking OK. So here it shows us a waveform. To see this average value, I am clicking the average value. So here this is the actual current display. So what is the current displayed is here 2.I1 is equal to 2.07 into 10 power minus 1. So I1 is equal to point. So from the simulation what we get is I1 is equal to 0.208 amps and I2 is equal to 0.138 amps. And I3 is equal to 0.069. So if you make a sum of I2 plus I3, what we are getting is it is equal to 0.207. That is, I am making an approximation in the third decimal, otherwise we will be going to get an equal value. So I1 is equal to I2 plus I3. Here we have verified the Kirchhoff's current law. So we need to check whether this value is correct theoretically. So for that, how we need to do the manual calculation. So for this particular circuit, it's a very simple circuit. So to find the equivalent resistance of the circuit, now see R3 and R4 is in series. So R3 is in series with R4. So the equivalent resistance will be 185 plus 185, this is 370 ohms. And again coming to this path, whatever we have calculated is in parallel with R2. So what I need to do is now R2 is parallel with this 370 ohms. So we need to apply the parallel formula, which is so to find the parallel value, what we need to do is this 1 by R equivalent will be equal to 1 by R2 plus 1 by 370. On solving this, we will be getting the R equivalent as 123.33 ohms. So again, this particular resistance is in series with this 50. So the total equivalent resistance of the entire circuit is equal to this 123 plus 50, that is equal to 173.33 ohms. So this is the total R equivalent. So the total current flowing from this source by Ohm's law, the current is equal to the voltage by R equivalent of the entire circuit. So this is calculated by 36 plus 173.33, and this will be equal to 0.208 amps. This is the exact value of I1 that we have obtained from the simulation. So the same value we have obtained from the simulation, 0.208 amps. If I want to calculate I2 and I3, you should use the current division rule. So according to current division rule, the I2 will be calculated by the total current flowing into the circuit into the resistance of other path. So the resistance in the other path is 370, and the total resistance on the path is 185 plus 370. So this is the current division rule we will be using, and we will be getting this I2 as equal to 0.139. Similarly, I3 is given by I1, and it is 185 by 185 plus 370. So these current division rules are simple, and we will be getting the answer of 0.069 amps. So the same value we obtained in the simulation also. So this is how we are checking the Kirchhoff's current law. So for the Kirchhoff's voltage law, I need to measure the voltage. So I need to require to connect a voltmeter. So I want to measure the voltage across this R1, across this R3, across this R4, and across this R2. I need to measure this voltage. So I am placing 4 voltmeters, and then I am taking the wire and connecting the voltmeter across the component for which I need to measure the voltage. So all the voltmeters are connected in parallel with the component for which we need the voltage. And if we connected a wrong polarity, we will be getting a negative values in the voltmeter or ammeter. So now I am just simulating this circuit after connecting the voltmeter. So it's giving an error, that is one VP1 is floating. So here it is not actually connected, it is represented by a R. So I am taking a wire correctly. The dark black dots give a correct connection. After giving the voltage connection, before simulating, we can give the name for each and every voltmeter. So this is the voltage drop across first resistor, and this is the voltage drop across second. So let me name as VP2, and here it is, it's a drop across third one, so VP3, and this is the voltage to measure the drop across the fourth resistance, so VP4. So I am displaying everything. So now I am saving the circuit. Then let us run the simulation, and let me take the 4 values and see the values, and I am clicking the average value to see the display. So I'm just copying the values which I am getting. So these are the values that we obtained from the simulation, and to check the Kirchhoff's voltage law, the 36 volt should be equal to the drop across R1 and R2. So our first equation is 36 is equal to VR1 plus VR2, that is VP1 and VP2 from the simulation. So if we add these two things, we will be getting exactly 36 volts. So the first loop equation is satisfied using simulation. For the second loop, the drop across R3 and R4 should be equal to the drop across R2. So if I add the drop across 3 and 4, we'll be getting 25.62 if you add these two things, and it is exactly equal to the drop across R2. So thus we are verifying it for the second loop also. So this is how we are checking the Kirchhoff's voltage law. And if we want to do this value theoretically, what we can do is we have identified, find the current flowing through each and every component. So this is a I1 flowing through this component. So the voltage drop across VR1 is equal to I1 into R1. So if you do the calculation manually, we will be always also getting the drop as 10.38. Similarly, we can do the calculation for all other resistance manually also, and we can check with the simulation result. This is how we can verify the Kirchhoff's law using PSIM. Thank you.